to decide what to talk about, and I then decided to maybe talk about something that might set a sort of new agenda in ice sheet processes and ice sheet science, which is the issue of groundwater underneath, especially Antarctica and Greenland. I'm of course not the only one who's been thinking about this a lot. So let me see if I can get my pointer up. So I've mentioned some colleagues here who've directly contributed to this talk kindly, but there's many others that I've had discussions with and have inspired the work. And it's very much so, if you look at the latest global groundwater inventory, which is what you can see here, this is from 2016. You can see that, you know, there's a big white space in Greenland, and Antarctica doesn't even appear on this map. But at the same time, you can imagine, you know, if you now put an ice sheet on one of these aquifer systems here, continental scale aquifer systems, then intuitively you would certainly expect there to be quite vigorous interactions. And the question is, you know, is this currently happening underneath Greenland and Antarctica? And if so, does it affect the ice flow and ice sheet processes more generally? And so what I thought I would do is just kind of summarize what, at least to my best understanding, we currently understand about groundwater underneath Greenland and Antarctica. And then my last slide is basically trying to set a few agendas as to where we might want to go in order to explore this further. So yeah, so at the moment, as you all know, we have pretty poor knowledge of groundwater's existence in Antarctica and Greenland and its impact on ice sheet processes. Although, as I found out, especially as I was updating a previous talk, there's quite a lot of new knowledge that's come out in recent years, which is very exciting. So much of this actually started, and there's a nice review here by Persson et al. In 2012 that lays out some of the history. Was that groundwater hydrologists sort of realized when they were analyzing the groundwater signatures around previous ice sheets, like the Laurentide ice sheet or here in Europe, that a lot of them had like depleted glacial meltwater signatures. And that got them thinking about potentially, you know, basal meltwater being generated and then being stored in these big sedimentary basins, which are the basins that you can see in pink here. And this has led to quite a lot of modeling studies over the last couple of decades or so, which are sort of shown by these bullets here, the white bullets, numbered bullets, of interactions between the former ice sheets and the sedimentary basins underneath. And so what I was going to focus on first is just the Williston Basin here, which is kind of was one of the probably best studied kind of sort of paleo ice sheet type situation. So I'm going to show you a profile that goes from A to A star here, so from left to right here, which is the Great Plains aquifer in the Williston Sedimentary Basin. Goes from, as you can see, Manitoba through North Dakota and South Dakota here, just for reference. And so during the Pleistocene, we had a growing Laurentide ice sheet here, which basically, you know, pushed across this big Williston Sedimentary Basin, which according to Wikipedia, I had to look this up, is around 15,128 feet thick, which according to my calculator on my phone equates to 4,611 meters. And what we have here is a number of aquifers, which are the white layers, and we have a number of confining units, which are the darker layers here. And as you can see, there's these arrows pointing away from the ice sheet, and the idea is very much that as the ice sheet is growing, we have meltwater being generated and being pushed very deep down into this sedimentary basin. And then as we have ice sheet retreat occurring and the situation to no ice sheet like we have at the present day, the hydraulic gradients will reverse and the water will start flowing back again, and will start basically well, coming out, I guess, at the surface, or if you still have an ice sheet on top, will basically come out in the basal environment. And this is pretty much what a lot of what I'm talking about today is all about. And then there's some little sort of smaller scale anomalies within the system here as well. And so here's a subglacial lake indicated, and that kind of sort of sets the scene for the next slide and some of the other slides that are coming up, because at least according to these simulations here, a lot of the interactions are focused on subglacial channels between the basal meltwater system and the groundwater aquifers underneath. So here you can see the ice surface, here's the basal till layer, and then we have a subglacial sedimentary basin with an aquifer in it underneath. And so during times of ice sheet advance, like the Pleistocene, we have high hydraulic heads that are pushing water out of these subglacial channels or lakes into the subglacial aquifer to store it there. And then when the ice sheet starts retreating, then the hydraulic potentials change fundamentally, which then causes the aquifer waters to flow back into the channels here, and therefore basically start feeding the basal groundwater system. And in fact, just to say that I'm, with the ideas here, I'm not reinventing the wheel. For example, Gwen Flowers had a fantastic model here where she modeled the Numerical Icecap in Iceland, and especially the interactions between basal water flow and groundwater underneath in the fractured basalt aquifer and some sediments, depending on where we are here. And you can see there's some very complex patterns at the current, or in 2005 when the modeling was done, at the in the basal water system, and much more streamlined in the groundwater system. But then if we project this into the future, you can see the ice will start retreating, the water flow patterns will start looking very similar. And this might also then affect the river basin water supply and have other sort of water resource issues in Iceland. And in fact, there was a very interesting experiment, fortuitous experiment at Numerical by Jeffrey Bolton and others, where there was basically a pressure wave being observed on the glacier, allowing the glacier to basically advance forwards temporarily in the late 1980s. And so they installed a sensor array. I'm not going to go into detail now as to exactly what sensors in this location here. So you can see the distance from datum in meters here. So this is meter scale, and here is the height also in meters. So this is very shallow ice. So this is the glacier terminus here. And then as the ice was advancing, it basically started running over the sensor array here. You can see the ice glacier surface here advancing over roughly 150 days there. And again, I'm not going to have time to go through all the data in detail, but effectively the way that the data were interpreted were that during times of advancing ice, and especially when there was high meltwater production, the till was pressurized from above through these water conducting fractures here. That basically allowed the water to get into the basal environment and into the subglacial aquifer. And then during times of lower meltwater supply and further down the terminus here, basically the water started, due to the hydraulic gradients reversing, started coming back out and basically recharging the glacial till layer here. So I should have said the light gray colors is the till layer, the darker colors is the sedimentary aquifer underneath, or the aquifer underneath, and then we have the ice above it here. So obviously this is was a very fortuitous experiment, very shallow ice. And the question now is, do these sort of things also happen underneath deep contemporary ice in Greenland and Antarctica, for example? So we all know that fast ice flow in Antarctica and Greenland very often, especially Antarctica, as far as we know, correlates with the presence of subglacial basins of sedimentary rocks, which due to erosion and associated processes are the source of wet and slippery basal till layers. We can obviously also have till layers being built up during marine incursions and various over time and so forth. But generally speaking, subglacial basins of sedimentary rocks play a very important role in ice flow in Antarctica. And as I'm going to show you a little bit later on, I'm also pretty convinced that in Greenland, sediments might play a lot bigger role than maybe we've appreciated so far. The till layers are then lubricated by water from upstream sources, as well as frictional heating due to the ice flow itself. And if the kind of balance between flow and water varies, then we can end up with situations like stick slip and water pressure cycles and so forth. And as you all know, there's all manner of different scenarios we might imagine, and there's an awful lot in this here in these images alone that we don't really understand well at the present time. And certainly in all the models that we have so far, groundwater is commonly ignored. So similar in this Chiara summary here of the different bed models and the sort of till situations that one might envisage, it says near impermeable bedrock here. So even in these models, the groundwater here was ignored. And so we don't know whether this is a big mistake. It might not be, but it's certainly worth finding out, because there's also all sorts of other reasons for why groundwater might actually matter. So if we start by having a more detailed look at Antarctica, we can, so here's just for reference is Eric Rignow's very well-known ice flow map. And here is a map that Luli and Alan Aitken and colleagues are currently working on. So this is not currently in the public domain, but they were happy for me to show this. So Lou in particular is using machine learning techniques and associated techniques to figure out where we are very likely to have sedimentary basins in Antarctica, and all sorts of other geological phenomena as well. But I thought I'd focus on the sedimentary basins because they're particularly interesting in this context here. So red colors is very high likelihood. We have high likelihoods, as you can see, around the margins of much of Antarctica. But also here where we have the big Wilkes and Aurora subglacial basins, as well as across the South Pole here and into the kind of ice stream catchments here that are flowing into the Weddell Sea, like Recovery Glacier and so forth. But I'll say a few more words about this later on. So there's quite a few locations that will appear in the coming slides. Not necessarily a lot of detail, but I will mention these in various contexts that are basically shown by these white circles that you can see here. And just to complete that picture, so work like this from Stuart Jamieson and others has looked at the erosion potential due to basal sliding. And again, red colors is high erosion potential and therefore high likelihood of till layers appearing, and yellow maybe not quite so much. But nonetheless, we can see again, especially around the margins of Antarctica, we have very high erosion potential and therefore the likelihood of till layers appearing. And we also know from many studies, that very exciting studies, I should say, that much of Antarctica is probably wet at the base. So here I've just picked a map from Stephen Livingston and others, where of course, again, we don't know whether necessarily this looks exactly like this, but I think we probably all agree that much of the base in Antarctica will have liquid water beneath it, and that's the key point. And so we clearly have all the ingredients that we need to have a situation like we had with the paleo-ice sheet models and the modeling that was done with those, to ask ourselves the question, so is the flow of Antarctic ice, and I'll say a few words about Greenland after this, modulated by groundwater, for example? Yeah, Olga, I'll talk about, sorry, I just looked at Olga's query on the chat, so I'll have a look at, I'll talk about that later on. The question is like, so is there groundwater being released from the subglacial environments to the basal environment underneath Antarctica and Greenland? And there we are. And so Paul Christopherson, Marion Bougamont and colleagues did quite a bit of work on the Cyprus coast, involving reconstructing the hydrological budget. And if we, for example, take the Camp, Mercer and Willans ice streams together, then at the present day, according to their modeling at least, roughly half the water comes from the ice sheet interior, a small component comes from local basal melting, but 45% for these three ice streams here seems to come from groundwater, at least according to their model. There's obviously a lot of question marks over this, but nonetheless, it sets a great agenda. And in fact, there's a study that's not actually much talked about, earlier study by Paul and Slavek, which is actually one of my favorite papers in the Annals of Glaciology, where they simulated freeze-thaw cycles of the some of the sediments beneath the cycle coast, beneath the ice streams there, and basically found that they had some really interesting feedback mechanisms with deeper groundwater circulation on a regional scale, which then regulated the thermal regime of the base of the ice, as well as the interstream ridges between the different ice streams. And so clearly this is some evidence here that there might be at least some groundwater contribution to the basal environment at the Cyprus coast. And Brad Gooch and others assimilated a bunch of aerogeophysical observations from the big and East Antarctic sedimentary basins, so the Wilkes and Aurora basins, and likewise managed to simulate some of the groundwater volume flux. So negative volume fluxes here are basically fluxes away from the ice sheet base into the sedimentary basins, and positive fluxes are the fluxes coming back up again into the basal environment. This is all dependent on the permeability of the sediments themselves, of course. But again, we have a situation where, as the Antarctic ice sheet was growing, a lot of the volume flux would have been directed into the sedimentary basins. And then as the Antarctic ice sheet started shrinking, a lot of this water is coming back out into the basal environment here. So we have groundwater depletion there. And you can see the time scales indicated here. And again, obviously, we need to bear in mind this is just a model with a lot of assumptions. But nonetheless, there's some evidence there that we might have groundwater flux coming back into the ice sheet base. And some of the key points here really is the time lags that we can introduce between, this water being pushed into the sedimentary basins and being released back to the basal environment a few thousands of years later. So this is something that we need to have a bit of a think about what that might mean. We also find, and I'll show you if I have time at the end, that there's a lot of geothermal heat flux being carried by the groundwater through advection itself. So it's one of the main agents of actually getting geothermal heat from depth in the crust towards the ice sheet base, which is obviously a very important consideration. And so amongst many other things, this also means that the sedimentary basins, being wet, upward directed hydraulic gradients, along with the heat flux, are basically conditioned for isostatic rebound for when the ice is unloading. And as I've, might potentially be a nightmare for ice sheet modelers, especially if you wanted to take this isostatic rebound phenomenon into account. But that makes it very exciting, of course. And so the question then becomes, how, if we want to look into the future, how do we want to go about actually measuring, these phenomena that, that might be indicated by the modeling studies we were just looking at here. And so in one of our papers a couple of years ago, we sort of tried to, outline the kind of techniques that one might use in order to do this. And so here I've just picked one of Atsu's papers, and Atsu's nice images from Pine Island Glacier, where we have the ice sheet terminus here above sediments of a few hundred meters thick, and then the basement here underneath it. And so the sort of things that we're already pretty good at, of course, is using airborne radar to look at ice thicknesses, to look at the thermal state of the ice itself and the ice base. I'll also show you an interesting study that was just published this year from Greenland using the new wideband radar systems that have just started appearing, coming up with all sorts of exciting discoveries. We're very good at using seismic reflection techniques to look at basal till layers and their mechanical states and hydrological states. There's also all sorts of exciting work from former ice sheet areas of using seismic techniques to characterize the signatures inside tunnel valleys, which has not so much happened so far beneath actual thick ice. So we're not yet sure whether this might work, but it's one thing that we need to figure out. And then we can use integrated airborne gravity magnetics and active source and passive seismic methods to actually look at the structures and geometries of these sediments here themselves. One thing that's missing here is a method that can actually look at the liquid water in these sediments. And for this, we really need electromagnetic techniques. There's no real other good way of doing that unless we use electromagnetic techniques. And that's something that colleagues have started using recently. It comes up with all sorts of exciting discoveries, and I'll show you a few more slides shortly. And then ultimately looking into the future, of course, what we ideally would need to do, and this is actually colleagues in hydrogeophysics in shallow aquifer systems. They're doing a lot of joint inversion work. There's an awful lot here that we can learn from that, where we can jointly invert all these data sets in order to get the best possible structures, best possible resolution on both the structures as well as the liquid water itself. Okay, so if the ice is a lot less than 1 kilometer thick, so we're talking about 700 meters here, that's sort of works perfectly for this. We can use transient electromagnetic techniques either on the ground or ideally in the air, because we can obviously cover a much larger area, using systems like the SkyTEM system here, operated out of Aarhus in Denmark. And they were able to fly in the dry valleys a few years ago. So here's a profile I will show you across, the one of the dry valleys here across Canada Glacier and into McMurdo Sound. And so here's that profile. You can see the colors is resistivity. So blue colors is low resistivity, highly conductive. These purple colors here is highly resistive, and therefore not so conductive. We have here distance in kilometers, just to give you a sense of scale, and here's elevation from plus 400 meters to minus 350. We can see highly resistive ice and Taylor Glacier, Sus Glacier, and Canada Glacier, and also the permafrost. So those are things that we already expected. But what was a big surprise was that we see these brine saturated sediments or very highly conductive groundwater actually all through the dry valleys here, all underneath the glaciers and all the way to McMurdo Sound. So that was a very exciting discovery with all sorts of implications, including subsurface habitats here, which is one of the earliest papers that came out by Jeremy Cookie and others using these data sets here. And I'll say a few more words about this later on. I'll swap to Greenland shortly, and then I'll kind of sort of loop back to tie everything together. And at that point, I will also mention the Farah Glacier in the neighboring valley here, neighboring dry valley, because there's a paper that came out again this year that actually showed some really exciting results from that. Okay, so this TEM, transient EM, works really well for a few hundred meters of ice thickness, but it doesn't work so well when the ice gets much thicker. And in that case, we need to use telluric techniques. And here I really need to thank Chloe Gustafsson, who's allowed me to use this slide here and the next one to show you how this might work. So telluric techniques basically use source fields that are being generated as charged particles come from the sun, bombard the ionosphere, interact with the ionosphere, and also some other electrical storms and so forth, and will create fluctuations in the Earth's magnetic field, which will generate plane waves, basically traveling through the crust and the upper mantle in the Earth. And when those plane waves hit conductive feature underneath the ice sheets, such as, for example, the groundwater, they will start concentrating and will start generating secondary electromagnetic fields, which we can then measure at the ice sheet surface using magnetometers and electrodes here, or antennas that you can see on here. So this is a nice schematic from a great paper by Kerry Key and Matt Secret. And so I'm very, very jealous about this, because Chloe, Kerry, Matt, and others were able to go to the Willens ice stream a few years ago, both to Lake Willens area as well as the more grounding zone area, the Willens ice stream, and collect a whole bunch of MT data. So you can see the MT stations in yellow here, arranged along transects to make this sort of pseudo 3D pattern across the lake, but also some other areas. And yeah, there's also all sorts of backup data from seismics and borehole measurements and so forth that they're able to use for their interpretations. There's a very exciting paper currently in prep, which I was lucky to read, but I can't tell you too much about, because there's a lot of surprises in that. It's just something for us to look forward to. But for now, what I wanted to show you is just to show you the general magnetotelluric results, to show you what the images look like. For this, please keep an eye on this lake outline here, which is this sort of big footprint there, because that now appears in my next page. So this black line is that footprint there, the leg outline. And then here is all the processed MT data across those transects that I showed you earlier. We broadly can see a 3-tier resistivity structure. So this is in log 10 ohm meters in this case, from very dark blue, which is extremely salty. So this we're talking like, so 1 to 2, 3, 4 ohm meters here, super conductive compared to most other places on Earth. Then around 10 ohm meters, we have lighter blue colors, which is fresh water. And then we have bedrock underneath, which much higher resistivity. And so as you can see here, pretty much we have everywhere in these images here, we have a lighter blue area directly underneath the ice, then a darker blue area underneath it, and then we're transitioning into this sort of yellow colors that indicates the bedrock. So if I look along this central profile there, is this profile here from left to right. And so Chloe's interpretation is that we have roughly 0.5 kilometer here of relatively fresh water saturated sediments. Whereas actually something's gone wrong in the labeling here because it says C2 salty groundwater, and actually this is the salty groundwater here. So that should have just said C1 and that's C2 there, which is another kilometer or so of what they interpret as salty groundwater. There's all sorts of question marks around this, and I'll come back to that later if I have time. But nonetheless, you know, there's very clear evidence for a lot of liquid water here underneath Lake Willans before we transition into low porosity bedrock. And we can see how we really lose resolution here because the really salty groundwater here eats up a lot of the electrical signals, and we're not so well able to resolve anything that's happening underneath it. Okay, so much for Antarctica for now. I'll come back to this. I'll wrap everything together at the end. I just wanted to show you a couple of slides for Greenland because there's been some really exciting work recently that's come out from there as well. So one of these papers came out this year using that wideband radar system I mentioned a little bit earlier. And so they're in the northwest of Greenland here and flew the system over the Hiawatha Glacier, which is, the ice is sort of up to just under 500 meters thick in the area. So here we're just basically focusing on the basal environment. So you can see the scale here, 20 meters that way, 0.5 kilometer this way. And they're basically found, so you can see the typical ice bed signatures here. So ice is in black above, and then the whiter colors is the ice basal layer interface here. But then beneath the ice base, they found this really bright reflector here, which the only way they can interpret this is basically as the groundwater table underneath the ice. And so this particular setting here is quite unique because this is the meteorite impact crater. I'm sure you will have heard about this beneath the ice in that situation here. And it's a really interesting paper because it interprets, you know, the interactions between the meteorite impact and generating the water table underneath and so forth. But effectively, there's two potential models that they have suggested might be the case. So either we have an unconfined groundwater table here, where we have a situation of ice above drained bedrock and then the groundwater aquifer underneath with an unconfined groundwater table there. Or an alternative model that might also work given the different radar signatures and associated work is where we have the ice above a frozen basal layer here, and then a groundwater saturated till that's pressurized and therefore has a potentiometric surface, and we have a confined aquifer here instead. And that, of course, kind of sets a nice agenda for potential future work. Some other work that we've done a lot of over the last decade or so is we've used a lot of active seismic and passive seismic techniques. So some of the work we've done, or Glenn Jones, who's a research fellow at Swansea, using Rayleigh wave electricity analysis on the Greenland seismic network. And so Rayleigh waves are particularly sensitive to shallow processes beneath the ice. So far, all the maps we've seen from Greenland, so basically stop at roughly 10 kilometers beneath the Greenland ice sheet and lose the resolution for the upper 10 kilometers or so beneath the ice, which for us as glaciologists in many ways is the most interesting area. And by using these Rayleigh wave ellipticity analysis, we can get around a lot of these limitations and actually look at the shallower crust beneath Greenland. This is a paper that's currently in review. Will hopefully come out sometime soon. But anyway, so at 1 kilometer, so if you take a depth slice through the crust at a kilometer depth beneath the ice, then we get this image here. And so what you can see is we've got very strong shear wave anomalies in some key regions. So for example, the Northeast Greenland ice stream here. So here in the kind of sort of Middle East, if you like, as well as here in the Kangerlussuaq and Helheim Glacier region, but also up in the Petermann region here in the Northwest. We also find these sort of anomalously low shear wave velocities, which were in the paper we basically interpret in terms of known potential existence of sediments, for example, beneath the Northeast Greenland ice stream or the Jakobshavn area here, or more fractured rocks in the southeast here. And this is actually something I will say a few more words about in the next slide as well. So all these regions have potential aquifer potential. The other thing that we're able to ascertain is that it was well known that the Iceland hotspot track basically moved across Greenland and generated anomalous geothermal heat flow. But again, those maps pretty much stop at 10 kilometers below the ice. And the question always was, does that anomalous ice actually reach the anomalous temperatures generated by that passing of the hotspot track reach the base of the ice? And according to our shear wave analysis, it certainly does. So here's an image at 5 kilometers depth where you can see the hotspot track, the classic track, extending from the kind of northwest towards the southeast here quite nicely. And also a lot of the seismic reflection work that we've done, especially in the sort of western parts of Greenland here, have all, like virtually all of these images have got sedimentary basins. So you can see the scale, they're typically a few hundred meters thick and a few hundred meters across. So where we have dips in the base of the Greenland ice sheet, we always tend to find that they tend to be filled with sediment. So again, there's a lot of evidence here for aquifer potential, which is, what's the bit that really matters for my presentation today. And so an interesting study in 2011 basically examined this southeastern region here, published by Dufour et al. And they basically did an offshore study and they found pore fluids coming out of the ocean floor or the continental shelf sediments up to 100 kilometers offshore that had the basal meltwater signatures. So again, was an amazing discovery to find this. And then basically, then actually before I should go further, I should say, so here's the transect you can see there. Here's the transect here. As you can expect, there's a somewhat complicated geology. What matters here, just for reference, here's the present day Greenland ice sheet there. Here's the ice sheet in the last glacial maximum there. Here's the elevation in kilometers there. You can see, and distance in kilometers along here from the ice sheets into the ocean, modern day sea levels there. And then what really matters is this subaerial basalt aquifer here. And according to the modeling they've done, this is where a lot of the action actually happens in terms of pushing water out from underneath the ice sheet, underneath the kind of modern day ocean here, where it then is able to travel up and basically appear on the ocean floor there. So here's one of these models they were able to run. You can see hydraulic head in colors here. So red is very high hydraulic head. Underneath the, so this is the last glacial maximum there. Much lower hydraulic head in the ocean area there. And this is pushing a lot of basal meltwater through this basalt aquifer until it basically comes out through these subsea floor sediments here and appears basically at the surface of these sediments there. And interestingly, at least according to the model, the basal meltwater infiltration and the submarine groundwater discharge are actually of very similar magnitudes, which means that a lot of this water being generated here actually makes its way through the basalt aquifer and actually comes out in the ocean. Of course, this depends on the permeability of the basalt, which is very poorly known, and again, clearly sets an agenda for what we might want to do in the future. And as you can imagine, this sort of submarine groundwater discharge was particularly vigorous during the last glacial maximum, and it's not quite so strong at the present day ice sheet. So a lot of the groundwater discharge that's now occurring in the region is occurring on land rather than in the ocean itself. And there's some smaller scale patterns here that are a little bit more complex. But again, there's a lot of evidence there for, basically groundwater being pushed deep into the crust and flowing out into the oceans. And in fact, there's two locations, and this is sort of very slowly sort of starting to pull everything together. And evidence for two locations in Antarctica that I'm aware of, where there was also submarine discharge of groundwater being found. One is in the dry valleys, which is what will appear on the left, and the other one is in the Lutzow-Holm Bay in East Antarctica here, which will appear up here shortly. So the first one is the Ferra Glacier that I promised you earlier, which, when I said, is a neighboring valley in the dry valleys. So here's another transient EM helicopter image profile. Again, we have pink colors high resistivity, blue colors low resistivity, glacier ice very high resistivity, elevation similar to what we have earlier, distance in kilometers along here. And again, we can see there's very conductive material beneath the ice. And then as we are approaching the grounding line there, you can see how this becomes much more conductive here and basically extends as a band underneath the floating ice there. And this actually looks very similar to the kind of environment that we might find in deglaciated areas. So the SkyTEM system, for example, started many decades ago as a system to map the coastal aquifers in Denmark to look at saltwater intrusion into the aquifers to basically inform the water resources strategies. And these images actually look very similar to this here, which, basically got these guys thinking that, this again is evidence here for groundwater discharge from underneath the glacier, Ferra Glacier here into the marine environment there, with all sorts of implications for marine processes in terms of, discharging materials for habitats and so forth. It'll appear in my conclusion shortly. And the other study was a little longer ago, so this was in 2011. I think I forgot the date here, where there was an experiment on sea ice using sensors installed basically beneath the sea ice. And they have found a lot of evidence for submarine groundwater discharge, which is in these light gray colors here, and the ocean tidal height in black there. And so there seemed to be a correlation between the vigor of the submarine groundwater discharge, which had classic signatures of glacial meltwaters, and the ocean tidal height. There is a model being proposed in the paper for how that might work, but the conclusion overall was they weren't entirely sure. But again, this is a fascinating observation that I'd certainly be very keen to follow up on, given half a chance in the future. Okay, and so from a glaciological perspective, the fact that we seem to find quite vigorous submarine groundwater discharges appearing might mean that, when we have our subglacial channels coming out underneath the ice shelves, that groundwater could actually contribute to a lot of that discharge and therefore affect basal melt rates underneath the ice shelves and potentially the stability of the shelves by extrapolation implication. And then more from a sort of marine bioscience angle, which is what I was trying to communicate earlier, there's a lot of dissolved nutrients being released into the oceans and potentially fertilize the polar oceans, especially if you extrapolate that across the whole of the Antarctic and potentially Greenland. And there's also been some potential plans for storing waste beneath the Greenland or in Greenland, But there's a lot of concern, obviously, when the ice sheet starts growing again, that a lot of that might then spill out into the oceans, and certainly that seems to be the case according to the current models. So that's clearly not necessarily a good idea. Okay, so I was gonna talk a little bit about can MT data help with reconciliation of geothermal heat flux. I can see I'm very slowly running out of time, so I'm not going to spend too much time on this. But effectively, as many of you will know, there's different models of geothermal heat flux in Antarctica having been proposed, all of which look very dissimilar. There was a very nice investigation of the reasons for why these images might be so discrepant by Lösing et al. That came out last year. And they basically analyzed, they basically found that the Curie isotherm and the heat production are the dominating parameters in the thermal calculation. And that the use of incorrect models or sparsely available data, as is the case in Antarctica, will almost automatically lead to unreliable results. And therefore, we really need a lot more data in order to get reliable heat flow maps, which is probably quite intuitive anyway. And then what I already indicated earlier is that there's a lot of geothermal heat flux actually being carried by the groundwater flow itself. And that is supplemented, amplified by the radiogenic heat production itself. And so my point here is that MT data are actually extremely sensitive to geothermal heat flux. So we had a model we proposed in one of the studies that we published a couple of years ago here, where there's a roughly linear relationship between temperature and geothermal heat flux, because the ions basically in pore space in the groundwater will become a lot more excited when it gets warmer, and will start flowing a lot faster, and that will start decreasing the resistivity, which therefore will, if we can sense that with MT or potentially the transient EM methods, will give us a good handle on geothermal heat flux if we combine the temperature change models with the Fourier law here. So we've applied this just as a speculative study to Dustin Schroeder's geothermal heat flux map for Thwaites Glacier. And actually, as it happened a few days ago, a new heat flux map came out for Thwaites Glacier, which again, unsurprisingly, looks a little bit different, which emphasizes the point here that we need more methods and more data in order to really constrain the heat flux beneath Antarctica as well as Greenland. But the point is, if we sort of assume different thicknesses of a potential sedimentary basin beneath Thwaites Glacier, we know, so we're currently working, and so Tom Jordan talked about this at the AGU meeting on a geological template for the Thwaites Glacier catchment. That seems to show that the sediments tend to occur more in drapes rather than thick sedimentary basins. But nonetheless, we can basically calculate the bulk resistivity ratio that we should get between the bottom of the sedimentary drapes and the ice bed, and also the temperature between the ice bed and the base of the sedimentary drape. And what we can see is, for example, if we assume a sedimentary thickness of 1 kilometer, we can see that for a situation where we have a very high geothermal heat flux, so that's some of the highest flux we can see in Dustin's maps here, we would get a bulk resistivity ratio of about 0.3. But even if we have average geothermal heat flux of 114, according to Dustin's map, we still get a bulk resistivity ratio of about 0.4. So still that is extremely detectable basically by MT methods. And therefore, integrating the MT data and the sensitivity that we have to the geothermal heat flux with the seismic measurements and others should really give us in the future a much better handle, hopefully, on the geothermal heat flux. Okay, and then my final slide is this one here, where I've basically picked on 5 areas where I felt that sort of future groundwater exploration might be particularly useful or fruitful in the first instance. So again, this is obviously Matthew Mulligham's and others' fantastic new bed machine map of Antarctica, of the basin. And here's the map of the sedimentary basin likelihood again. And so, unfortunately, a lot of the field work, of course, has been delayed by initially logistical challenges and then being hit by COVID, so a lot of these things haven't happened yet. But there's the ITGC project underway, where we will acquire a lot of active passive soil seismic data, gravity data, MT data, and associated data sets. So that's going to be a fantastic data set to really look at, the potential for groundwater underneath Thwaites Glacier and the potential geothermal heat flux, and improve existing maps basically by generating these high quality field-based data sets. So that's already funded here and will hopefully happen starting in the 2022-23 season. Then we're also lucky to get a major NERC grant with a few colleagues, so Martin Siegert, Paul Christophers, Marin Bougamont, Andy Smith from BAS, and others are involved in this, where we're going to be able to go to the Institute Ice Stream and Bungenstock Ice Rise to acquire a lot of seismic data as well as MT data to look at the structures in the big sedimentary basin underneath the Institute Ice Stream, the distribution of groundwater in the basin, and then try and model what effect that might have on the ice flow and the stability of the region there. Because a lot of, according to a lot of Martin's and colleagues' work, the Institute Ice Stream and the whole region in that area here is potentially perched on the threshold of stability. So any smaller scale changes might potentially have quite strong implications for the ice flow and the mass balance. And the same is true for the Foundation Academy system. So Neil Ross is currently leading, some of you might have seen his IGS seminar last year, for example, is currently leading a big review study of the system here. We've found there's a very high sedimentary basin likelihood in this whole area there that potentially reaches all the way to the South Pole. And again, if you combine this with a very deep trench that we have underneath the Foundation ice stream, really gives the ideal conditions for groundwater being generated, heat flux being concentrated, and then potentially, together with a retrograde sloping base, to potentially really have an impact on the ice flow and its changes in the future. So that's worthwhile having a look at. Then in the Australian Research Council has funded two major centres of excellence, one in Melbourne called CEF, and the other one in Hobart called ACES. And they're basically collaborating together to have a major field season in the Denman Glacier system in the future. We've in fact just had a review paper here that we've just on Sunday submitted to the CRIS for discussions, which will hopefully appear soon, that basically sets the scene for a lot of this work here. Because again, there's a high sedimentary basin likelihood, there's a connection between Denman Glacier, the Aurora Basin here. As you all know, it's got the deepest trench in the whole of Antarctica, which is very likely to focus the geothermal heat flux simply because of the natural geothermal gradient, but also potentially because of thermal refraction phenomena, which makes groundwater very likely, and potentially groundwater Denman Glacier interactions and so forth. And so again, this is certainly a fantastic vehicle to do a lot of MT work and seismic work in the future to investigate that. And then the final study here, so Audrey Huerta and Paul Winbury have already got an NSF grant funded. It's also been delayed, unfortunately, like everything else, due to COVID and logistical challenges. Here in Oatsland and the Wilkes Basin, high sediment basin likelihood is one of the largest regions of Antarctica below sea level here. So even smaller scale changes potentially have large sea level implications there. And yeah, obviously a high sediment basin likelihood. And again, this is certainly a region that's very worthwhile focusing on in the future. And in fact, Hobart organized a workshop focused on Oatsland last year, where there's a lot of really interesting results or thoughts being presented that are available online on their website if anyone's interested in this. Okay, and with that, I apologize for running slightly over time, but we started a few minutes later. So thank you very much for listening, and obviously happy to take any questions.
Thanks ever so much, Bernd, for a fascinating talk. There are a couple of questions in the chat. I think perhaps Laurie Padman asked the question So he's asking, he did not follow the isostatic rebound comment and its relationship to groundwater fluxes. I'm not entirely sure what part of the talk that was
Okay,
from.
it was fairly early in the talk. You had a slide that had the isostatic rebound comment on it. And I kind of understand isostatic rebound, but it seemed to be, you went through it fairly quickly, but it seemed to be in the context of freshwater pathways, groundwater pathways.
Yes, yeah, no, I remember. So again, it was more of a sort of setting a hypothesis or like a speculative comment in terms of, you know, not having a sedimentary basin that's basically filled with water, with hydraulic gradients, basically pushing the water upwards, as opposed to having, you know, a basically frozen water underneath the ice sheet or no water at all. And so that, but I mean, I haven't obviously seen any modeling on this underneath Antarctica regarding the isostatic rebound, but certainly, you know, if you have a sediment basin filled with like warm liquid water, we'll have a different isostatic response compared to, you know, if you had a situation where there's no sedimentary basin or sedimentary basin that's basically filled with basically frozen water. That was what the comment was all about. But there was no particular kind of scientific study behind that comment. That was more of a sort of setting the scene for this is maybe something that we should be thinking about in the future.
So were you thinking of the entire bed rebound being different because there's a sedimented layer on top, or were you thinking more of expansion of the sedimented layer as the amount of water in it changes?
Yes, I mean, I was thinking more about the, you know, if you have several kilometers of sedimentary basin filled with liquid, relatively warm water, it's more the isostatic rebound of that whole basin rather than, you know, the till layer or just the shallow system directly beneath the ice. So I'm just talking more about the sort of few kilometers beneath the ice sheet in the sedimentary basin itself.
Okay.
It's a good point, though. I should maybe look into the literature a little bit more to see or to try and see whether, you know, it's possible to quantify that comment a little bit more, because it's a very interesting phenomenon to look
at. Thanks, Laurie. We also have a question from Vivian. Vivian, would you like to unmute if you can?
Yes. One question was, do we have any idea how extensive the under the subglacial drainage system is that is wet based? You know, do we have any idea of that? What parts of Antarctica would be underlain by wet or potentially, you know, where there may be some active flow? Because you mentioned some of the areas, but I mean, have we actually mapped it out? Do we have a distribution of that, you know, as in a map?
Yeah, let me get back to the, so this was the map I showed earlier here from Stephen Livingston and others, which assimilates a lot of the observational information and puts that together with hydraulic or hydrological reconstructions to basically make this map here of the base of the Antarctic ice sheet, where you can see the lakes, which are obviously these blue dots here. You can see that the deep lakes are in purple and the shallow lakes are in blue. And then you can see the kind of pathways that were modeled to connect those lakes with each other. So that's, you know, as far as I'm aware, obviously there's been follow-up work since then, which has maybe updated some of the regional information. But this map to me certainly set the agenda as far as, you know, what a potential water system might look like underneath the Antarctic ice sheet. Don't know whether that answers your question.
Yeah, okay. I guess that went by fast. I may have missed that map.
Yeah.
And the other question I had relates to geothermal anomalies in West Antarctica, and what relation, if any, there might be to subglacial volcanism or any igneous activity.
Yeah, so there was, let me just get back to the Thwaites map I had a minute ago. So there's a volcano here in this region there, and there was also some really interesting work by Elen Serussi a few years ago on the impact basically of the hotspot underneath West Antarctica on the ice sheet base. And the interesting thing is that the paper I mentioned that came out last week on an updated geothermal heat flux map of at least the Amundsen Sea region of West Antarctica, that actually shows a very dichotomous geothermal heat flux beneath the Thwaites Glacier, where the northern region has a lot less geothermal heat flux, and the southern, sorry, no, when I say southern, I meant kind of, I always get confused about what's north and what's south in West Antarctica. But basically the eastern part here of Thwaites Glacier had a lot less geothermal heat flux, whereas the western part here of Thwaites Glacier in this region had a lot more geothermal heat flux. And this is where we've got this volcano system sitting here, for example. So I should have maybe put that reference up. I don't think I've written it down here, but it's definitely worthwhile having a look at, because it really has this sort of dichotomous geothermal heat flux across Thwaites Glacier, with a lot less flux in the north, in the east compared to the west over here. Helen Serussi's paper on the impact of the hotspot on Mary Birdland and the region around there is also very worthwhile looking at in terms of interactions between the crustal heat flux and the ice sheet itself.
Thanks, Vivian. I think next is Frank Patton.
Oh yeah, thanks a lot, Bernd. It's on the SSB map, which is intriguing, of course. So I wanted to know briefly what are the different parameters that go in there to establish that. I mean, if you use all these algorithms, I guess an obvious one is bed topography. But what are other parameters that are used?
Yeah, so I must admit that off the top of my head, I'm not entirely, I wouldn't be able to list them all, unfortunately. I can see that Olga was very interested in that as well. It's certainly something I can find out. I know that, as you say, is the basic topography. I know there's a lot of, all of the gravity data from Antarctica has gone into this. I also know that Lou and Alan have assimilated a lot of the seismic information that was available. And I think those were certainly the key data sets. And I know that Alan feels that gravity exploration in particular is extremely useful in this kind of context. But I'm probably missing one or two data sets that have also gone into it, which I don't recall right now, unfortunately. But because there's existing geological knowledge from various previous maps that has also fed into this, and then they're all combined together in some manner using these machine learning techniques. I'm not claiming to be an expert in any of this at all. The guys, luckily, they kind of kindly got me involved in this after I gave a pre-version of this talk at the IGS seminar in July last year. I was desperately trying to find a map of sedimentary basins underneath Antarctica. I couldn't find one. And then I talked to Alan Aitken and Martin Siegert about this, and that sort of spurred them to start working on this. And that's sort of what's ultimately generated this map that we can see there. So my intellectual input has admittedly been relatively minor, apart from coming up with the original idea that we really need a map of some sort. Yeah. Thanks, Frank.
Thanks, Frank. We have a comment from Gavin about a typo on your.
Oh, okay. Yeah, I should definitely fix that one.
was the last slide. Do we have any final questions? There's a minor comment from Laurie about the discussion between you and Frank.
No, it was really about looking at that transect there. So I was trying to understand.
Sorry.
I was trying to understand what the dark blue seaward of the flotation line really meant. What physically are we looking at in that layer there?
So I think like once you get to the floating part of the ice here, this is simply the signatures of the ocean water, I think. So that the ocean water is obviously extremely highly conductive, the saline water. And I think, you know, the base where it's cut off, I think is pretty much where they lose the sensitivity in the EM inversions themselves. And so everything that we can see here in blue is pretty much just the ocean water.
Okay, I thought you were implying that that layer was a continuation of the blue that was inland of the grounding line, but you were just saying that because there is some liquid water flux inshore of the grounding line, that whatever it's carrying will get out to the floating into the open ocean.
Yes, yeah. So I must admit, I haven't really had a chance to read the paper in exact detail, but I do understand from their interpretation that this area on the grounding line here, or certainly looking at the resistivity image, looks very much like a classic sort of coastal aquifer system where you have, you know, like the more saline water, ocean water, interacting with the fresher groundwater in this sort of coastal region here. I'm not sure how much evidence they have for how exactly these interactions might be happening, but I do understand from the paper that they have good arguments to say that there is groundwater discharge across the grounding line. I must admit, I'd have to refer back to the paper now to recap exactly what those arguments are.
Under certain circumstances, you'd have the ocean water being forced into under the grounded ice, right?
Yes, yeah. Yeah, so the classic sort of groundwater saline water interface, you know, that obviously has the saline water pushing underneath the freshwater aquifers, and I think this is sort of part of the interpretation that they have here as well.
So I'm just wondering if I took a water sample right near the grounding line under the ice shelf, what would I be looking for to see whether there was groundwater coming out?
Yeah.
And
yeah,
maybe the answer is on the, however, Lutzel Home Bay measurements were made. I need to read that paper.
Yeah, see, I mean, by both of these, so this Lutzer Home paper here, so they had an installation of sensors actually on the ocean floor, so that was deployed through the sea ice. I was tempted to show an image of that, but then I thought, you know, I didn't want to clutter my slide up too much. But it's a really interesting paper to have a look at because you can see the sort of seafloor rig. There's a very nice explanation of it that they used in order to basically monitor the water quality on the ocean floor. That basically gave these data that you can see on this plot here. And I must admit now, I looked at this paper when it came out last week, but I can't recall exactly now, I must admit, what the exact argument was for the groundwater discharge across the grounding line, other than making a mental note that was pretty compelling. Yeah, it's worth having a look at, certainly.
Okay, it looks like Gavin answered my question about what to look for. 018.
Okay. Excellent. Yeah. Sorry, Laurie. I should recall that study better, but my mind's gone a bit blank, unfortunately.
Thanks, everyone. Do we have any final questions? Just give it a minute. Someone might be struggling to unmute the microphone. Laurie says thank you.
Thank you, Laurie. There's an awful lot of detail, obviously, and I've gone through an awful lot of material, tried to simulate it, and there's obviously an awful lot of detail that I haven't mentioned. But to me, there's certainly an awful lot of really interesting questions that have arisen by from putting this together, and a lot of future agendas, I think, to go and investigate.
Thanks again, Bernd, for a fascinating talk. I think we should probably close off around now, let people get on to their next meetings and what have you. Thanks again for speaking, and I really look forward to uploading this to the interweb. And thanks everyone for joining us. I hope you have a great rest of the day.
Okay, that's great. Thank you very much, Craig, again for the invitation. It's been a pleasure.
Cheers, everyone. Bye for now.
Bye.